Now we will look at a special instance of this. We will make compositions of the type cosine of some constant times x and sine of some constant times x. And clearly, so sine is this function here, and cosine is this function here. Maybe we can try hiding them. Well, why is there still a cosine? Well, it's because it's the derivative of the sine function, right? No, it's because I can't hide both of them at the same time, sorry. Anyway, now we just have them all here. The point is that if you take sine and find the derivative of that, you get cosine. And if you take cosine and find the derivative of that, you get minus sine. Agree? Now, what if we look at a function which is f of x equals cosine times something x, or something times x, and g of x equals sine of something times x? Then things start looking slightly differently. So let's just try making this k equal to, say, 2. What does this function look like? Which of these is it? Basically, it's the cosine of 2x will be this one, only shrinked somehow. And the same goes for the sine of 2x. I mean, note what happened with my x-axis, right? I have adjusted it so that my x-axis, the units down here, change. Agree? That's why we don't see a scaling visually. It only happens in the numbers down here. So cosine of 2x is this one, and sine of 2x is this one. Now the derivatives you see here, the derivative of sine 2x is this function up here, and you can see that it's bigger than 1. Why? Well, because this has a bigger slope than the original sine of x. And likewise for the cosine, here we have the cosine, and the derivative of that is this one. We could also choose a very small k. This means that our functions, I mean, here you have to move a lot, right? Now this is almost 3 to get anywhere. This means that the slopes are less. And if we use the chain rule, we'll see that it's basically just that we should take the constant inside, put it out in front, and then we should have this inside. Why is that? Well, it's just the chain rule, right? The chain rule tells us that if we have an inner function and an outer function, we should take the outer function, find the derivative of that. What is the outer function in the case of g, for example, here? Well, it's sine, right? So what is the derivative of sine? Well, it's cosine. What is the inner function? Well, it's k times x, so we should just have that inside. Then we should also remember to multiply by the derivative of the inner function. The inner function was k times x, so the derivative is just k. So we multiply by k and put it on in front. Then we get this. I just want to say that, I can't remember if I've done that. Yeah, I have. Now if we pull this k down to this k, which is pi over 180, right? What is that? That's the number that we use to convert degrees into radians, right? Had we defined our sines and our cosines using degrees instead of radians, what would have happened? Well, whenever we found the derivative of the function, we would have to zoom in a lot to find them, because you can see the derivatives are almost impossible to see down here. So that's another reason why using radians is a clever thing. This means that when you take the derivative of your sine and cosine, the derivatives look like something that is comparable to the other function, right? The scale is the same. So the derivative of sine and cosine, if you plug in degrees instead of radians, are these slowly varying functions that you almost can't see.